Okay, we're finally ready to make our nameplate. The first step is to mount the blank to the top of the jig using the 1/4 28 Allen cap screws. These are tightened using an L-shaped wrench called an Allen wrench, and make sure to tighten these screws very hard, otherwise the part can move during the machining process. The next thing we're going to do is mount the bottom of the jig into the vise. The lower left-hand corner of this jig is our reference corner. We're mounting it on the left-hand side, sticking out of the vise a little bit so that we can use an edge detector to determine exactly where that corner is located. The center of the nameplate is 4 inches to the right and 1 1/4 inches up from that corner. When tightening it into the vise, make sure you tap on it. Here is an edge detector. It is a 2/10 of an inch diameter tip that is spring-loaded and attached to a shaft. It's often called a wiggler. The idea of an edge detector is you spin it at 1500 RPM and you approach it with the edge of the part that you wish to detect. As you approach the edge detector, at some point, the edge detector will start to spin eccentrically. The idea is to keep approaching the edge detector until you can detect that specific moment when the edge of the detector encounters the edge of the part. Once you are happy with the edge detection process, it is time to zero the machine. This is done by hitting the yellow X button. 0 comes up, you hit enter, and you will effectively zero the X-axis. Once the X-axis has been zeroed, you must play the same game in the Y direction. It is important to realize that if you overshoot the edge detector, it is necessary to back out the part all the way until the edge detector starts spinning true again, and then you can reapproach the part and try again. Once you're happy with the Y edge detection, we will also zero the Y-axis by hitting again the yellow Y button and entering 0. Since the edge detector is 2/10 of an inch in diameter, it is necessary now to move the machine 0.1 inches in both the X and Y direction. In doing that, the center of the spindle will coincide exactly with the corner of our jig. Once we have done that, it is necessary again to re-zero the machine. So the machine will be re-zeroed on the corner of the jig. This drawing that I've created of the nameplate that I wish to make. Notice I have actual coordinate information. I have coordinates of various endpoints and start points of the arcs. The radiuses of the arcs are mentioned. The nameplate is going to look like that, and notice that this one large radius, 6 inches, is well outside the actual page that the drawing is printed on. And notice that the center of my drawing is 0, 0. Here is the completed nameplate that I plan on making. And let's describe a little bit how it's going to be made. This particular one is made out of plexiglass, so it's clear, although the one we're going to make is going to be made out of aluminum. The first process that we're going to do is we're going to have the face cutter, the fly cutter, come across the surface of the nameplate and make it flat. Now, we're not going to program this particular part of the assignment. That is going to be something we do at the machine right before we run the rest of the program. So for your case, let's not worry about it. The next thing that's going to happen is a 3/8 of an inch end mill is going to come along, and it's going to start here, and it's going to go along the entire piece, and it's going to do what's called profiling. It's going to cut out the aluminum plate in several passes until it takes on the shape of what you saw in the drawing previously. After the profiling operation is completed, this little radii that goes along the outside to create this nice little edge is going to be done with a ball end mill. So a ball end mill is going to come in, go around the part, and put that radius in there. The final process will involve the engraving. Using a very small end mill, we will engrave the letters mechanical rocks will be put in there. So right now we're going to go through the processing steps required to program the machine to make this nameplate. When you're a machinist or when you're working on a part, you have the dimensions of the part, not the dimensions of where the tool needs to cut to create that part. So here is a drawing which indicates one possible strategy in which to profile our nameplate. The end mill would start off here. It's always rotating clockwise, mind you, looking down at it. The end mill would start here, approach the part, and then go in. It will go to the left and cut out the outside dimensions of the nameplate, and when it's finished it will retract. When this occurs, the center of the spindle will execute the path indicated by these dotted lines, and it will leave behind the actual nameplate that we've designed and we've conceived of. So that it's important to realize that all the dimensions on the milling machine are referenced to the center of the spindle, so that when the cutting takes place, if you're using a 3/8 of an inch diameter end mill, you must offset the end mill 3/16 of an inch, the radius of the end mill, away from the part that you're cutting. Of course, you have the dimensions of the actual part that you wish to create. It is a very difficult and painful process to go back and figure out what the dimensions of a 3/16 offset are. So the machine gives you the opportunity to use this thing called cutting radius compensation. In this particular example, we are using what's called cutting radius compensation to the left. In other words, we're going to program the part's geometry into the machine, and the machine is going to automatically offset the tool by its radius, and it's going to offset it to the left. And the word left means that if you imagine riding on top of the end mill, it's going to be moving to the left, and it gets offset to the left, and that's why they call it cutting radius left. This kind of milling is called climb milling. The cutting strategy is to use what's called cutting radius compensation to the right. This is also called conventional milling. Now in this scenario, now keep in mind the most important thing to realize is the tools always rotate in a clockwise direction for cutting. And that's the way the tools are designed. The flutes take the chips up and out. But you are allowed to go to the right as well as to the left. So in this scenario, the tool will go up, it will go to the right, come around, and finish the profiling process. Now there are certain advantages to using climb milling, and there are certain advantages to using conventional milling. It turns out that when climb milling, the cutting tool moves a little bit away from the part. It actually gets bent slightly away from the part, and in conventional milling, the cutting tool moves into the part. So in climb milling, the part is left ever so slightly larger than the actual size you want, and in conventional milling, it is left slightly smaller. Now keep in mind, this is a big cutting tool. The one we're using may be smaller, but despite the fact that you might think that these tools are incredibly rigid, they actually are capable of being slightly bent during the cutting process. And there are other issues regarding the differences between climb and conventional milling. But for the most part, another aspect of it is the finish you get. It turns out that climb milling gives you a better finish. We decided to cut out our nameplate using cutting radius compensation to the left, or climb milling, and this decision's been done to make a better finish. The plan is to have the tool come down here,
Move into the part, follow the dashed line path of the tool, and then come back to this point. We're going to take 4 rough passes and 1 final pass to complete the cut. Remember, with cutting radius compensation, we program the actual part's dimensions, and then the machine will compensate for the radius of the tool. So it is essential to have an extremely good drawing that has all pertinent endpoints and start points of arcs, as well as their radiuses, as well as, of course, you have to know where the center 0, 0 is. Once again, we're in the computer lab where we're using the offline software for the Analam controller. It simulates the software exactly as it appears on the actual CNC interface. So when it first comes up, you see control software. Number 1 is what we're going to select. And once again, notice we've created this little template that has the function keys, and we will hit F5. We are now going to hit the F2 button for program, and we're going to hit the create button, F2, and now we're going to type in a program name, which I will call nameplate 3. When I hit enter, nameplate 3 comes up on the menu right there, and we are going to then select it with the F6 button, and then we're going to hit the edit button, F4. Once again, and we've seen this in MDI mode, the last line is always the end of program line, and as we add lines to the program, they will appear above this line. It always goes above the cursor. Now, since we've seen this before doing the MDI mode, I'm going to do it rather quickly. The first line of my program is going to be the selection of units, which is the number 7 button. Make sure the numlock button is on. The 7 key brings up, once again, the inches, which is what I want. The plus sign toggles between inches and millimeters. I select inches and I hit enter. I'm now going to select absolute coordinates. Now the way you do that is you hit the Alt-E key, and once again, the absolute, the plus and minus sign goes from increment to absolute. I'm going to select absolute, and our program is already building. The first thing I want to do is grab a tool. Remember, the first thing we're going to do is profile the part. The tool that I'm going to select is going to be tool number 3, which was going to be a 3/8 of an inch end mill. I am going to type. The number 5 button is for the tool. I'm going to select number 3 for the tool. And if you recall from the previous video, M6 is the tool change command. So we will enter that into our program. The next thing I want to do is get it spinning at a good RPM. Again, the period button on the keypad brings up the RPM screen. I'm going to enter 3000 and hit enter. I am now going to move the tool to its entry point. Once again, according to the drawing, this coordinate is y equals negative 1.125. This is the bottom of the nameplate, which is probably y equals negative 1.25, and I want to enter somewhere below that. So my entry point will be y negative 2, x0, y negative 2. I'm going to rapidly move to the coordinate. Now, rapid is number 1 key. It is x0 and y negative 2. I will come down in the z direction in my next move. I'm now going to hit another rapid move, which is the 1 key again, and I will now enter 0.1. I am getting ready to cut right now, At this point, I could turn on the coolant with the command M8. So again, it's the M code, which is the number 6 key, and I could enter M8 if I wanted to. Because I actually want to put the coolant on manually, I'm going to actually delete that line. You go to it and you hit delete. Tool number 3 is going to be a 3/8 of an inch end mill. However, because I want to take some rough cuts for the first 4 passes, I'm going to enter a diameter slightly larger than 3/8 of an inch into the tool table for the first 4 passes, and then I'm going to enter the correct diameter for the final pass. Now I want to put a comment in the program. The way I do this is I go to the miscellaneous F9. I then hit F2 for comment, and up comes my comment, and I'm going to say tool 3, 3/8 end mill, but 0.385 in tool table. The comment appears in the program with an asterisk in front of it. So it's going to be a 3/8 of an inch end mill, but I'm going to enter 0.385 in the tool table. I have moved the cursor back to the bottom line so I can continue to enter code. Now we've moved the tool down to 0.1 inches, and now we have to actually take our first pass. I'm going to make this a line move now. So instead of rapid, a line move is the number 2 key. And I'm just going to bring it down to negative 0.1 inches in the Z direction. I'm going to feed at 20 inches a minute. The first thing is going to be moving the tool from here to here. This is the coordinate y, negative 1.125. Once again, I'm going to enter a line move. The number 2 key on the keypad brings it up. We're going to move x0, y negative 1.125. And I don't have to keep entering the feed rate, but at this point we are going to invoke the cutting radius compensation. Now the plus key will toggle you from left, right to off. We are compensating to the left. Very important step right there. So there it is, tool left. Our first move is going to be an arc, a clockwise arc from this point to this final point here. It has a radius of 6 inches, so that's going to be the next program line. To program the arc, we push the F5 key. The milling program, under the milling program, there is arc, F4. We push the F4 key, and we are entering the arc by way of a method in which we enter the endpoint of the arc and its radius. It is a clockwise arc. The endpoint is x negative 2.7666. The y is negative 0.4491. And the radius is 6 inches. The next section of our arc is going to be this little one from this point to that point. Its radius is 0.125 inches. Once again, I type the F4 key for the arc. It brings up the arcing program. It is once again a clockwise arc. Its endpoint is negative 2.7905. The y coordinate is negative 0.2434, and its radius is 0.125. I will just show the entering of one more line. We're going to go from this point to that point, and this time the radius is 0.321, and it is a counterclockwise arc. Once again, we hit the arc. The plus sign will let you toggle from counterclockwise to clockwise, or clockwise to counterclockwise. The coordinate of this endpoint is negative 2.7905. The y is 0.2434, and the radius is 0.321. I've entered all the lines of code now, and I've come back to my start point. Now this is an important point right now. I'm going to retract the tool back to my y-2 starting point, and that's when I'm going to cancel the cutting radius compensation. Otherwise it won't actually go back to that point. This last move brought me back to the end of the part. I'm going to enter one more line move to retract the tool to the original place, and hitting the plus sign I'm going to go through the choices until I get to tool compensation off, and that completes my cycle. I would like to draw the program now to verify it, but before I do, since I'm using cutting radius compensation, the tool table must be correct. So I will hit the F6 key, and I will notice that tool number 3, I have entered a diameter of 0.385 for tool number 3. The reason is because I want it to be a rough cut. Let's just briefly go over the program as it stands. We picked inches for our units. We're using absolute dimensions. We first pick tool number 3, which is a 3/8 end mill, but we enter 0.385 in the tool table. We get it up to 3,000 RPM. We rapidly go to the point 0, -2. Then we come all the way down to 0.1 inches above the surface. And at this point, we invoke line moves instead of rapid moves, and we're feeding at a rate of 20. We come down -0.1, and now we enter the part. So the first line move brings us to the y-1.125 inch part, and all of these arcs are what comprises the geometry of the profile we wish to make. The final move is we come back out to the x0, y-2, and we turn off the cutting radius compensation. We now want to draw the program and verify it. We hit F2, and we hit the display. Well, we look at the view that we want. I'm going to take a top view, which is what I want, and the display I'm going to hit on the menu fit, I'm going to hit enter. Now when I do that, let's look at the drawing. That looks perfect. I've exited out of the draw part of the program, and I'm back into the editor, and I want to quickly look at these lines. Now I'm going to be repeating these lines, and I just want to look at what line I want to start repeating at. Line number 9, where I bring the tool compensation left on, that's going to be the first line I want to repeat, and I'm going to go all the way back down to line 19. That will be the last line we're going to repeat. So we're going to add a few lines so we can take progressively deeper cuts into this part. So I'm going to add a new line here. A line move will be z minus 0.2. And now I'm going to tell it to repeat. The repeat button is under the mill function, F5. Repeat, I think you can see, it is listed under F8, repeat. And up on the screen comes the blocks that we want to repeat. We said it was going to be line 9 through line 19. And when we enter it, it will put that into our program. So basically we profile the part, we move down another 1/10 of an inch in the Z, and then we profile it again. I've added the lines to do all the profiling. I come down 1/10 of an inch 4 times to a final depth of Z minus 0.4. And now I want to do something a little bit different. I want to make a final pass, and the way I'm going to do that is I'm going to tell the machine to grab another tool. It's actually going to be the same tool, but I'm going to enter in the tool table the correct diameter of the tool. That will give us our final cut. Let's take a quick look at the slight changes to the program. After we make our last rough cut, which is at a depth of Z minus 0.4, we now make a tool change to tool number 6. That's going to be still the 3/8 of an inch tool, but it's going to have the correct tool diameter listed in the tool table. It does everything that we did before. We spin it at 3000, we rapidly go down to our entry point of x0 and y negative 2, and then we finally bring it down to our final depth of negative 0.5, and then we repeat one more time the entire profiling. And that should give us a final cut that's just a little bit of material being taken off. We should get a really good finish out of this. I just want to point out that so I don't get too confused, I've put a comment line on line number 27 indicating that that 3/8 end mill has the proper diameter listed in the tool table. Let's draw it again to see if we're getting the passes we want. You can see it's going to make 5 passes, and the last pass should have been a final pass. Now we're going to take a little look at some of the options on the drawing menu. If we go to display, the F5 key, you notice one of the choices there is window. I'm going to select window. You go back up to the drawing screen, you're going to see a little window in there, a box that's going to close up on a particular part. I'm going to look at this edge to see if we are getting a final cut. And now we will hit enter to have it redrawn. Now we're just looking at the very bottom edge. Those are the passes. And we should see a final cut a little bit closer. It's hard to see, but you can see that final cut was slightly in more than the other one. Changing the view to isometric, we can see the outline being made. The next step is to grab tool number 4, which will be the ball end mill, and we'll have it come along here to create the scalloped edge. Now the way we do that is we don't use cutting radius compensation. The actual tool, the center of the tool will be hugging the edge of the part, just like this, and that's how we will get the scalloped edge. Hope everybody can see what I'm talking about. Okay, once again, let's look at the lines of code that have been added. We are asking for line number 34, a tool change to tool number 4, which the comment line below it shows it as a 1/2 inch ball end mill. The M3 code is clockwise direction of the spindle. We spin it up to 3000 RPM. And then we're going to, again, exactly like we did before, rapidly move to 0, negative 2, come down to 0.1 above the part, and then we're going to go down another 0.05 inches. And then we're going to start our profiling again. This time it's going to not involve cutting radius compensation. I moved back up to the lines 9 through 19. Now these are the lines that contain the geometry of our profile. I am going to copy and paste them. I want to just go over one more time the strange way this works. But you hit the F1 key for more. You enter the mark line, and then you just mark all the lines you wish to copy. And then I hit more again. I come down to copy. Notice the screen says block saved. And now I move my cursor down to where I want those lines copied to, which will be right over there. I hit more one more time, and I do paste. And up comes the profile geometry. And it is now on line 41 that I begin everything. I'm going to hit enter so I can do a bit of editing. And the only thing I want to change is the word left to off. So I'm going to come down here, again the plus sign ratchets through all the choices, and off is what I want. And now I'm just going to quickly look at all these lines. Now, I turn the cutting radius compensation off in line 51, which already is off, so I'm fine. I want to verify the program again using the draw feature. I am going to look at a top view. Again, this is the outside profiling being done in 5 passes, 4 rough cuts, and a final finishing pass. And then the next pass was with the ball end mill. Notice that since the radius compensation has been cut off, the tool has moved over the radius of the tool. And this, in fact, will be the edge of the part. This will actually be the edge of the part. So there we are. I've added a couple more lines of code. I really want my little scalloped edge to be 1/10 of an inch deep. Now this is an aesthetic choice. 0.05 looks good, 0.1 looks pretty good. I've gone with 1/10 of an inch, and it turns out that I have to repeat lines 41 through 51. So line 53 shows the repeat command, and the one thing I am going to warn you about with the repeat function is if you add lines to this program now, the repeat command does not take into account that you've added up lines. So be very careful if you add lines or edit this program. The number of the lines that you're repeating may also have to be changed. That's something you have to do. The machine isn't going to do that for you. Let's do one more verification using the draw command. Again, 5 passes to do the outside profiling, and now it should be 2 passes with the ball end mill, and it looks good. Switching to the isometric view, you will see perhaps a view a lot of people prefer to see is isometric sometimes, and it looks good. Let's look at some more lines of code I've added. Now the final operation for us is the engraving operation, which is going to be tool number 5. That is going to be a 1/16 of an inch ball end mill for engraving as indicated by the comment line 55. Once again, we started spinning at clockwise direction at 4,000 RPM. This little end mill likes to spin pretty fast, otherwise it'll break. I am guessing the start point of the engraving. I'm not really sure how long the letters are going to be. I'm guessing a coordinate of -2, y.1 as the start point for the word mechanical. I'm going to use the draw program to check whether or not that's a good place to begin. So we'll find out in a minute how good a guess I made. Now to do engraving, you go to the mill program, which is the F5 key. And at that point, you then hit the More button, which is the F7 button. And up comes a menu that has several choices. That last choice is Engrave. I'm going to move down and select Engrave. Now when the engraving menu comes up, this is a very simple one to use. The first thing we enter is the text. So I'm going to enter the word mechanical. There's no spell check here. If you get it wrong, it will engrave a misspelled word. Again, my start point, I took a guess, was -2, y.1. I'm going to select the start height. That's where the tool is going to start from, 0.1 inches above the surface. The depth is going to be extremely small, 0.01, -0.01 for the depth. If you go more than that in one pass, you will break the tool. The height of the letters is the actual height. I'm going to make 0.4 high inch letters. Now keep in mind, the higher the letters, the longer the word as well. These things all go together. I'm not angling it and I'm not mirroring it. I'm going to feed at a rate of 10. If you feed much faster than that, you will also break the tool. Okay, once again, I need to verify how close to being centered my engraving is. You want the top view for this particular one. When I hit run, we're going to see the entire program now. The profiling, the scalloped edge, and now the engraving. As you can see, the word mechanical looks to be slightly to the left, but it's fairly well centered, so I'm just going to make some adjustments. To move it over to the right, I have to make this number more, let's say, like -1.8. The Y looked good to me. Again, verifying the draw program. Having made the adjustment in the starting point, moving it over a little bit to the right, I feel fairly good about that. That looks nice. Okay, I brought up another engraving line. So it's mechanical rocks, so now I have to type in the word rocks. There is no choice of font. The X start, now rocks is a much smaller word, so perhaps the X coordinate is more like -1. The Y has to be below the center line, so perhaps I'll try -0.6. The start height again is the same. The depth is again the same as it was in the last one, -0.1. The height of the letters is 0.4. Of course, you could change it if you want. The feed rate's important to be 10. Again, to verify it with the draw command, push the run button, and we'll see how close to being centered the word rocks is. Now you can see rocks is fairly well centered, but it really should be moved over a little bit to the right. Having made some adjustments, let's just see how it looks. Everything looks good. Okay, let's review very quickly the program we just wrote. The first line, we select our units to be inches. Our second line, we are using absolute dimensions. We select tool 3. The first thing is a tool change command, M6. This is a 3/8 inch end mill whose diameter has been entered as 0.385, a little bit bigger so that the cutting radius compensation retracts the tool a little bit further away from the part. I had left out the M3 code before for clockwise rotation, so I just put that in. So we have clockwise rotation. The RPM is 3,000, and we wrap it down to our start point. We then come down Z -0.1 at a feed rate of 20, and we do all of our geometry. After we do our profiling, we drop down another 1/10 of an inch each time. Since it's absolute coordinates, Z is going to get incremented to -0.2, and we keep repeating it. Then -0.3, we repeat the profile, -0.4, etc. To do the final pass, we change tools. Now, we're not really going to have to change any tools, but this is just so that the tool table enters the correct diameter of the tool for our final pass. We come down, we make our final pass at -0.5 inches, and we will have finished the profiling. We then switch to our ball end mill, tool number 4. Our ball end mill makes the exact same geometry with the cutting radius compensation turned off. With cutting radius compensation turned off, as shown on line 42, the center of the spindle hugs the exact edge of the part, so we'll end up with a nice scalloped edge. We do that with 2 passes, one at Z -0.5 and then the last one at Z -0.1. And now we switch to the 1/16 of an inch ball end mill for engraving, and we simply bring up the engraving algorithm. So the program's quite simple, and we're ready to run it. Let me just say one thing that's worth mentioning. I had left out this line here in the program, the M3 code, to turn the spindle on clockwise. When I added that line, it shifted every line down 1. And believe it or not, I had to go in now and change all of these repeat lines, which used to be 9 through 19. They all became different. Now they're 10 through 20. And then my final ball end mill repeat line also changed. It was 41 to 51. It became 42 to 52. So unfortunately, this is a disadvantage of using repeat commands. But just be aware of it. If you add lines of code after you use a repeat command, you better change things.